this fantastic webinar tonight with Dean Wampler and Tathagata Das, but you can call him TD. Dean is our big data architect at Typesafe, and when he's not traveling around giving talks and trainings, he likes to build scalable, distributed big data applications using Spark, Hadoop, and other things. He's also the author of several books, including Programming Scala 2nd edition and Functional Programming for Java Developers, all from O'Reilly. TD is a committer and PMC to the Apache Spark project and lead developer of Spark Streaming at Databricks. In the past, he spent time at the AMP lab at UC Berkeley researching the heck out of big data and working on Spark Streaming. A couple of quick announcements. I'm going to hit the poll for you right now. We're going to ask a question, one question about which technologies you're currently using, so that'll take up the screen. Please vote accordingly for those of you that are logged in with a computer. We'll collect questions for the post-presentation Q&A in the Questions tab of the GoToWebinar control panel. There's going to be a couple other polls that we'd like to launch along the way, and hopefully we'll get those out of the way in just a minute or two. So thanks very much to Dean, thanks very much to TD and Databricks, and finally, as always, the big shout out goes to our happy Typesafe Project Success subscription clients, without whom none of these webinars would be possible and my roof would probably continue to leak. So without further ado, I am very happy to hand it over to Dean and TD.
Okay, this is Dean. If you would bring the view back up. There it is, the presentation. So TD is going to drive this thing, so when you hear me say next slide, that's what we need to do. And what we're going to do today is go through 4 things about Spark Streaming. Really, it's more than 4, but just sort of organize the talk. And if you could give me the next slide, TD. So here's our outline. We're going to start with just a big overview of stream processing today, in which Spark Streaming fits. And then TD is going to give a very detailed deep dive into Spark Streaming, how it works, and in particular focus on features, especially recent features that help prevent data loss and make streaming more robust. Then I'll finish with a section on just some more general architecture tips that you should keep in mind when building streaming apps that include Spark Streaming. And that will be it. And so I'll hand it over to TD to do the next section. Oh, sorry, I'm actually doing the first section. So if you'll go to the next slide. Okay, let's look at the stream processing landscape. And basically, it sort of breaks down into 3 groups of things. The first being the actual processors that work with your data to, modify it, clean it, transform it, store it. Usually, these are the things that are ingesting raw data that have to be very resilient against, whatever's thrown at them. You've probably heard of several of these already. Storm is a very popular system for single event processing, building networks of processors. There's a tool out of LinkedIn called Samza that integrates nicely with Kafka for this purpose. Of course, we're talking about Spark Streaming today, and people also sometimes use Akka for building these kind of data ingestion and transformation systems where you need event at a time processing. Next slide, please. The next one is storage. So this slide is actually meant as places where you would, say, drop data when it's done, but as we'll see, there also can be sources of data that you might process. Obviously, one of the big ones these days that we're seeing a lot of interest in is Kafka. As another LinkedIn tool, it's sort of thought of as a message queue, but it's really more of a log-oriented data aggregation system. The unlabeled icon on the right is Kinesis, which is a similar system available for Amazon Web Service users. People also store data in HDFS, of course. In Cassandra and React are 2 very popular data storage systems for this kind of data. There's others I could have put on here, like HDFS and the Hadoop environment. And along with HDFS, people also use other distributed file systems like S3. Next slide, please. And then sources of data can be all of those that I just mentioned, but also these other ones are things that are built right into Spark Streaming already. You can ingest data out of 0MQ. out of Flume, which is a very popular log aggregation system that was written at Facebook and is used a lot in Hadoop systems. The icon on the lower left, the Ethernet connector, was the only thing I could think of to use to indicate aggregating data from sockets, which is a pretty popular thing to do. MQTT is a message queue standard that's designed specifically for Internet of Things, and there's a listener available in Spark Streaming for that. And then finally, it's pretty popular to ingest the Twitter firehose and analyze that data. Next slide, please. Okay, now TD is going to take over and talk about how Spark Streaming works.
All right. Hello, everyone. As people have already said, I'm usually referred to as TD, and I'm going to talk about Spark Streaming. So for those who are not yet familiar with what Spark Streaming is, it's essentially a scalable fault-tolerant stream processing system. And the way it differentiates from other stream processing systems is three things. One is it provides very high-level API that often joins Windows comes out of the box, which is often 5 times less code than other systems where you would have to implement these things on your own. Then there's the whole stream processing system. Even if it's distributed, it is completely fault tolerant. You can get exactly one semantics if you configure it the right way, and that is what I'm going to talk about in this presentation. And then the third thing is, and probably the most important and useful thing in the bigger picture, is that its integration with the whole Spark ecosystem. It integrates with machine learning libraries in MLlib and SQL processing, data frames, graphics. This whole ecosystem things makes it a very attractive option that is unique in the whole stream processing landscape. And obviously, as Dean has already mentioned, it can take data from a whole bunch of sources and push it out to file systems, databases, dashboards, etc. Going down a level deeper, the way Spark Streaming works is that Spark Streaming has these things called receivers. And receivers, as the name says, receive data streams and chop them up into small batches. You can configure the size of the batches, 1 second, 2 seconds, 5 seconds, whatever. And these batches of the streaming data is now then handed over to the core Spark engine. The Spark engine processes the batches and pushes out the results to whatever downstream systems, database, or file systems that you want to push it out to. So that's the high-level overview of how Spark Streaming works. So to start with a very brief example of how a program in Spark Streaming looks like, let's say you want to count the number of words received in every batch using data from Kafka. The way you would start is your program is first by defining this thing called streaming context, which is the entry point of all streaming functionality. And there you specify some configuration and, the most important, the size of the batches. In this case, I'm going to start with 1 second batches. Then once you've defined the context, you can now create this thing called dstreams. Dstream, which is the short for discretized streams, is essentially represents a stream of data in the Spark Streaming library. And you can create a dstream from Kafka, for example, using these utility libraries that we provide with Spark Streaming called Kafka utils. And what it will do is create this dstream which represents all the data coming from Kafka from a particular topic, whatever you configure the dstream to get, and this dstream is represented by this variable called lines. Now you can apply these transformations on these dstreams. For example, in this case, I know that the dstream is composed of lines, and I want to split them up into words. So this functional transformation essentially it's very Scala-like, so it should be fairly intuitive that it says that take every line and split it into words, and which essentially creates another dstream called words. And then you can keep doing these transformations like map and reduce by key to count each of the words in each batch. And then finally, we're going to say that print some of this counts on the screen so that I can see what's going on and have a look at the data. It will print that data some of the counts on the screen as an example of what's what is the data that the the stream is actually receiving. But as all these lines are, when these lines are executed, everything is lazy. Nothing actually occurs. To actually start the whole processing of receiving the data and processing the data, you actually need to tell the context to actually start. So this, and when you do this, that's when the system will start the receivers and start receiving the data and processing them through these transformations. And if you look at the full program end-to-end, that is essentially it. That's all the code that is, which is much less code than a lot of many stream processing systems out there. Because and we achieve it because of its nice functional nature that we learned from Scala and stuff. Anyways, so jumping into the next part, which is the main meat of this talk, is what are the features in Spark Streaming that help prevent data loss? And to understand that, let's first take a slightly deeper view of how Spark Streaming works, which will help us to understand the fault tolerance features that are present. And before we even come to Spark Streaming, let's look at Spark in itself. Any Spark application actually runs in this model of there's a Spark driver, which is like a master. And when the user, all the code that the user writes using Spark is actually runs in the driver. When that code is actually executed, what the Spark driver will do is that it will ask for resources from any Yarn, Mesos, or Spark standalone cluster. It will launch executors, Spark executors in the cluster based on the resources that have been given, and it will then it will use those executors to actually execute tasks that does all the data processing. So the Spark driver will send these tasks to the executors, and the tasks will read data, process them, write it back to HDFS or something like that. So this is common to all Spark applications. Spark Streaming is definitely a Spark application, so it runs in a very similar model, but it also has some additional components that runs because of its streaming nature. So all this code that we showed, the word count code, it will run in the driver, but when you actually start the streaming context, the driver will run these long-running tasks which will run the receivers in them. So here we created a Kafka D stream, so it will run a Kafka receiver in one of the executors, which will take the data stream from Kafka and keep receiving the data, and then dividing the data into blocks. So these blocks are basically blobs of data which is stored in memory. Along with storing the data in memory, it will also replicate those blocks into another executor for fault tolerance. I'm going to explain that later in the next few slides. But the data is essentially replicated between two executors. And then periodically, every batch interval, remember we had set it as 1 second. So every 1 second, the driver will launch tasks to process these in-memory blocks of data. And then the final process results is pushed into any data store or database or file systems, etc. So that's a slightly deeper view of how Spark Streaming works, how is the receiver run, how are the data blocks organized in memory. Now with this understanding, let's look at how the fault tolerance and reliability aspects of Spark Streaming. So people may ask, failures, why even care? And the reason we have to care about failures is that many real-life streaming applications need zero data loss guarantees, despite any failures in the system. For example, you are building, let's say, a fraud detection system for a bank. You do not want any of the transactions to be dropped on the floor because you might be missing out on fraudulent transactions. So you have to ensure that every transaction is actually processed by the system. And within this requirement for zero data loss, there are often two types of guarantees that different applications want. For example, some applications want at least once guarantee, and it is sufficient to that every record be processed at least once. So some records may get processed twice or thrice. It is okay for that application in that case. Whereas other applications, for example, bank fraud detection system, may want exactly once guarantee, which is a stronger guarantee that every record is processed exactly once. No duplicates, nothing, exactly once. So based on these guarantees, the system, the Spark Streaming application needs to be configured and built in slightly different ways, and that's what I'm going to talk about next. And in this context, there are two kinds of failures that broadly kind of sums up all the kind of failures that can happen in the system. And one is a failure of the executor and then failure of the driver. These are the two major components in the system. So obviously, these are the two things that can fail. And we're going to discuss how the system handles these different kind of failures and what you will have to do to make sure the system handles that. Okay, so let's start with the simpler one where an executor fails. So let's say if an executor fails, all the receivers running on that executor will be lost. All the in-memory data blocks will be lost. So what happens next? So what the driver will automatically do is detect this failure, and the driver will restart the tasks that have been lost, the receiver that was lost on a different executor. And remember, we already replicated each of the data blocks. So those tasks will be restarted on this other executor, which has those replicas still around. So, and this will happen without any user intervention and without any user explicitly configuring anything. So the driver will take care of executor failures in this manner by restarting the receiver and restarting the task on the block replicas. The more challenging question is, what if the driver fails? Because if the driver fails, all the executors are killed. So all the receivers are dead, all the in-memory blocks are dead, all the computations are lost. So how do we recover from that? And for that, what we have provided in Spark Streaming is this mechanism called D-stream checkpointing. And what it essentially does is periodically save the whole graph of D streams that you have set up, all the mapped reduced by key, that DAG of D streams that has been set up, all that is saved periodically to a fault-tolerant storage, so that when the driver is actively running, all this information is saved to HDFS, and you can use that checkpoint information to restart the driver if the driver fails, and the restarted driver can then launch new executors and the receivers once again using that checkpoint information and continue where the system had left off before the driver failed. So this ensures that the system can be recovered on failure, given if the driver fails. But to do this, you have to ensure that the driver process is restarted automatically. To configure that, these are the things you need to do. So first of all, you need to enable the D-stream checkpointing. Of course, one, you need to configure the automatic driver restart, and all cluster managers, Yarn, Mesos, Spark standalone support this. I'm going to talk about that in the next slide. Then second, you need to set a checkpoint directory in a HDFS compatible file system, so that all the checkpoint information is stored inside that directory. This is pretty easy to do. You can just say streaming context checkpoint and give it the directory path. And the most critical thing is you have to slightly restructure your application code so that it can use checkpoints for recovery when the whole process is restarted. Again, I'm going to explain that. So let's first talk about how to configure automatic driver restart. In Spark standalone, you can very easily use Spark Submit. Spark Submit is the standard way of submitting Spark applications. And there you can specify this thing called cluster mode, where your driver process is also going to be run within the cluster. And then the Spark standalone mode, the cluster itself can monitor whether the driver is running or not, and it can supervise. Yeah, you also have to mention this dash dash supervise to tell it that supervise the driver process and restart it when it fails. So then the cluster itself will take care of automatically restarting your failed driver process and stuff. All the configuration you can see in the online Spark program on the Spark standalone guide. For Yarn, Yarn automatically supports it. Again, you have to submit it in the cluster mode, and you can take a look at that Yarn configuration to see how many times it will be restarted on failure and stuff. In Mesos, Marathon is often used to restart, to submit jobs inside Mesos, and there too you can configure how that your driver process will be restarted automatically. Cool. The third part is restructuring your code. So if you take a look at your any Spark Streaming application, there are essentially two parts to it. One is the part that creates and sets up the streaming context with all the dstream transformations. And then the second part, which actually starts the streaming context that has already been set up. To ensure that whenever this application is restarted and this whole code is executed once again, the system can recover from checkpoint information. You need to restructure it in this way. First, put all the creation and the setup scripts all the creation and setup code inside this function. We'll call it the creating function. It's essentially like a factory function for providing a fully set up streaming context. And there you also have to specify what is the checkpoint directory that you're going to use. So all that setup code has to go inside this function. And second, now you can use this function in this traditional helper method that you provide called get_create, where you provide the HDFS directory for where the checkpoints will be written, as well as the creating the factory function that you have written. And you can, so the semantics of this get_create is that if the HDFS directory that you have provided has checkpoint information, it will recover the streaming context from that information. Else, if the information doesn't exist, it will call the factory function to create and set up a new context. So in this way, if this process is restarted, it will automatically figure out whether to actually start from scratch or restart from an old checkpoint information. This makes it easier for application to be to handle automatic restarts and stuff. So the other some users may have already observed that even if we restart the application, the blocks of data that were in memory has not been recovered. They were lost. So how do we recover from that? And for that, we provide this additional mechanism in Spark Streaming called write-ahead log, or it is often called journals and stuff in other systems. But what it does is that it synchronously saves all the received data, the data received by the receiver, to fault-tolerant storage. So essentially, the blocks of data that is kept in memory is also written to HDFS. And what this allows is that the blocks persist across driver failure. So if the driver fails and it gets restarted, the system can continue recover all that blocks from the HDFS where it is stored in HDFS and continue processing without losing any data. So this to enable this write-ahead logs, you need to do these 4 things. One, first of all, you need to enable checkpointing by setting the checkpoint directory, because all this the write-ahead log and the block data is written inside the checkpoint directory as well. Second, you need to explicitly enable the write-ahead log in the Spark configuration by saying this, by setting this particular Spark.streaming receiver write-ahead log enabled to true. And the reason that this is not enabled by default is that many streaming applications don't really care about setting don't really care about actually, they are tolerant towards losing data. So we don't enable it by default, and people can enable it only if they want those higher level guarantees. Third is that the receiver that has been written should also be reliable. And by reliable, I mean that the receiver should be smart enough to acknowledge the upstream source that the data has been received only after the data has been actually written reliably to the wall. This is to ensure that data is either written to the wall or the upstream system is going to replay the data in case of any failure, so that you don't have, so that ensures that no data will actually be ever lost. Either it will be recovered from the write-ahead log or be replayed from the source. And the fourth thing is you need to disable in-memory replication of the blocks, because the data is already getting replicated in the HDFS file system, and so you don't really need to replicate it in memory. You can set the storage level, you can explicitly set the storage level to not use replication for all the input streams. Okay, so there is another additional mechanism called RDD checkpointing that is sometimes useful for doing stateful stream computations, but I'm not going to talk about that in the interest of time in this talk. But at a high level, what it does is that some stateful computations can have really long lineage of GARDDs. So currently there is this abstraction called RDD, which ensures fault tolerance, and by keeping track of the lineage of the transform data. For stateful computations, this lineage can increase infinitely, which is pretty bad for fault tolerance, because you don't want to recompute infinitely back in time to recover stuff. So RDD checkpointing saves the intermediate data to HDFS to ensure that you don't have to recompute all the way back till beginning of time. So there is more information about RDD checkpointing in the online streaming programming guide. Go take a look. Right? Let me move on to the fault tolerance semantics that these mechanisms provide in total. So as I've already said, zero data loss means you need to provide at least once guarantees despite any failure. And now you can, if you think about the whole stream processing pipeline, there are three sections to it. One is the receiving, the other is the transforming of the received data, and then finally outputting, which is pushing out to external data stores. Now, I'm going to explain what the semantics are for each of these stages. So for transforming, since it is based on the Spark's RDD model, which it ensures that all the transformations are exactly once. That is, as long as the received data is present and can be recovered either from memory or from write-ahead log, the final results that needs to be pushed out will always be the same. So the transformation stage is always exactly once guarantee, as long as the received data is not lost. The outputting part, where the final computed results is pushed out to external data stores, that you can configure it to achieve exactly once guarantees, because if the outputs are idempotent or transactional. So if it is idempotent, so even if the task that is actually pushing the data out to an external data store is restarted because of any failure, it doesn't matter, because it will write the same data once again, because it is idempotent. But if your computation cannot be expressed in an idempotent manner, you have to make it transactional, where you have to push all the data out using a transaction so that the data gets committed to the external data store exactly once. So, but that is up to the user to actually figure out what their application logic is, whether it's idempotent or not, and accordingly configure how they can push it. But once you have done it this way, you can make the outputting stage exactly once. Now the receiving stage, sorry, my bad. The receiving stage, is gives only at least once guarantee, because data may get replicated to the write-ahead log, but the upstream system, let's say Kafka, may not have the acknowledgement that the data has been already received by the time the system actually can fail in the middle. So there may be duplicate data that can come from through Kafka if you are using write-ahead log. So overall, the system gets at end-to-end semantics of at least once, because the receiving stage is at least once. But if you at least, yeah. So with the with the checkpointing and the write-ahead log and the reliable receivers all put together, the total end-to-end semantics is at least once. But if you want a stronger guarantee that you can of exactly once in an end-to-end stage, you can achieve that with this new Kafka direct approach that we introduced in Spark 1.3, which treats Kafka like a replicated log itself. So it doesn't need a separate write-ahead log. It just uses Kafka like a log and then reads it pretty much like a file system. And so it does not have to use any receivers. It just grabs the data directly from the write-ahead log, like, as if it is reading a file. You don't need to create multiple D streams for parallelizing the reading. You can just union. You don't have to care about any. You don't need to enable write-ahead log. It's a much simpler approach, because Kafka is already doing the hard work of replicating and keeping the data as a log for you already. And if you want to learn more about this approach, you can take a look at the links when the slides get published. And with this, you get exactly once guarantees in all the three stages, and which means end-to-end semantics of exactly once. All right. With this, I'm going to hand over back to Dean for continuing the presentation for design tips for successful streaming applications. Back to you, Dean.
Thanks a lot, TD. That was great. This is a fairly short section to wrap up, but before we go into this, we have a second poll we'd like to present, and Oliver's going to do that for us. There it is. We'll give you the right answers here in a second. It was a joke, of course. Also, we're collecting questions people are answering.
This is Oliver. I just wanted to let you know we've got a pretty good list of questions so far. Thanks everybody for chiming in on those, and please continue to send. Depending on time, we'll try to get to all of them, but do pop them in there and try to make them as specific as you can. And if there's a specific slide or technology to reference inside the question, please drop that in too. We'll leave the poll up for just another 15 or 20 seconds while everybody gets on it. Looks like the majority is software, the vast majority, and then pretty evenly split between the rest. All right, I think we've got what we need. Let's get back to the presentation. Thanks everybody. We'll do one more at the very end, just as a farewell. Back to you, Dean.
All right, thanks. As soon as the slides come back up, there we go. All right, so this is more of a we've heard the deep dive details about Spark streaming, so here's a few other things to think about as you're building an entire system, the whole architecture and all that. So just some brief lessons and principles that are useful. And it may basically fall into these three categories: using additional components in the architecture to make the resilience even better, making choices between whether you right or when you need per message handling, and then some work that's coming in Spark Streaming that ties into the so-called reactive streams standard or systems like that. So next slide, please. Okay, so systems like Storm and Akka and Samza are really designed to let you do individual message handling when that's appropriate. And there are times when you want to do that. You get some sort of alert, you want to trigger a response, fire off a pager, whatever. Spark Streaming obviously isn't designed for that, but it is designed for what seems to be sort of the 90% case where people aren't necessarily interested in handling individual events so much as reducing the time between data arriving in the system and information being extracted from it. And so that's when Spark Streaming is really great. And it has another benefit in that because you're reusing all of the existing infrastructure for RDDs, for data streams, and Spark SQL for machine learning and GraphX and so forth, it's a great solution for the Lambda architecture where you might have two parallel tracks of data processing, one that's doing streaming, one that's doing batch. A common problem in that architecture is that if you're using entirely different systems for each of those segments, then you often end up implementing logic twice. You don't have that problem with Spark Streaming. You can do both of them with the same logic. Just it's all about setup and teardown, whether it's in a streaming context or a batch context. So it's really nice for that. And also, Spark Streaming tends to be a lot better for very high-scale analytics, much more so than, say, Akka, which is really designed for just high throughput, low latency, but not so much for massive scale of a big chunk of data that I need to work with. Okay, next slide, please. All right, the other thing that we see a lot, in fact, I was reading the slides for a talk at Spark Summit about how Netflix is using Spark Streaming and tools like Kafka, is to use tools like that in front of Spark Streaming to buffer the data in a reliable way. And TD got into this a little bit and showed the example with Kafka utils, so that even if all of the things that are now in Spark Streaming for some reason don't work for you, you can still go back and get the data out of a Kafka queue. So whenever possible, if you can be ingesting data from a source that can refeed the data to you if necessary, then that further ensures that you won't lose any data. And another trick too that I sometimes do is if I'm just going to store all the raw data anyway, like if I'm writing into HDFS and it's going to be my system of storage for all this data, then I'll just go ahead and write the data and then maybe ingest it from there to do processing. Sort of the idea here is that obviously anything you do in processing adds just a little bit more complexity, just a little bit more something that could go wrong. So if you can simplify the process of saving data, and this is effectively what the write-ahead log is doing, then you sort of separated concerns a little bit, giving yourself a little extra resiliency. So that's why I like to do that. Okay, next slide, please. So there's a new standard called Reactive Streams that some of you have heard of that's being implemented in RxJava by Netflix. There's now an Akka Streams implementation of it. And the gist of it is it's actually a very simple standard. All it really is about is a out-of-band signaling between the consumer of data and the producer to control the rate of data flow. And it solves two problems that you'd otherwise not really be able to solve very well. One is that if you have unbounded buffers between those two, inevitably you run something long enough, and some of these systems are designed to run for years, you'll hit some anomalous circumstance where there's just a huge volume of data all of a sudden. It overwhelms these buffers. You get out-of-memory exception, and then things crash. And the other possibility is that these systems just decide, well, I'm just going to start dropping data or sampling or something. I got to keep going somehow. You'd rather not have to have these little individual components making these sort of ad hoc decisions. You'd like to control the flow strategically. And then make strategic decisions about what to do when data flow is too much for the system to handle. And that's really what Reactive Streams does. I don't think I have the website on the slide here. Actually, it's on the next one. But you can decide, really at the micro level, let the two components discuss between themselves how much data they can deliver. Now in Spark 1.5, Typesafe is helping implement first back pressure, just in general terms, facilities for that independent of reactive streams, and this will be part of the core part of Spark Streaming. And then there'll be an extra add-on like the Kafka utilities, the Twitter utilities, and so forth that will let you connect to a reactive stream compliant stream for that particular mechanism. So it'll be really nice that you'll be able to just hook up a reactive stream directly to Spark Streaming and have pretty resilient flow of data with this back channel for flow control. Now that's not in there today. So in the last, basically I just described everything on this slide. Then on the next slide, let's talk a little bit about today with Spark 1.4. We'll go ahead and give me the next slide. There we go. So one trick you might do today is if you have a system built on reactive streams, just use Akka to provide a sort of not a choke point, that's really the wrong word, but a control point where it can use the existing features in Spark Streaming to make sure that it doesn't overwhelm the Spark Streaming job until this new capability is implemented. So in particular, let me see, if you go to the next slide. So for example, today you can set a max rate, which is it's a static value, so it doesn't give you sort of dynamic flow control like you'll have with reactive streams, but it does let you at least rate limit what's being delivered to the system. And you could use Akka to do this, where Akka then handles avoiding overflowing the system. Or there's other things you could do once you have Akka in the picture like that, but this is probably the easiest thing. Use the max rate as a rate limit property, and then consider maybe whether to buffer the data in front of Spark Streaming with something like Akka, or it could even be Kafka, something like that. But then once 1.5 is out, you'll have these extra options that you can pursue. And next slide, please. All right, we wanted to thank you very much for listening in, and I'm going to pass it back to Oliver, who will go over the next slide, which is some information that you might follow up on.
Yeah, thanks a lot, Dean. We can check out the next slide for a minute, TD. Thanks. There's a couple what to do next if you're interested in continuing this conversation. Databricks is available as a hosted platform on Amazon Web Services with a monthly subscription. When you receive this slideshow, you'll be able to click on these links there to follow up. And in case you missed the announcement, we at Typesafe, in addition to being a certified partner for developer support for Databricks, we've also enlarged our partnerships with Mesosphere to include Mesos and DCOS, so you can read more about it on that link. I think we've got one more poll. This is the final one, folks. Thanks very much for your participation in them. I'm going to put that up now, and I'm going to get the questions prepared for the guys. And we've got a pretty strong list of questions going on. Actually, Dean, since you'd been touching on this, a couple questions have come up. Rather, making how would you differentiate for us Spark streaming versus Akka streams versus Java 8 streams?
Okay. Yeah, they're pretty different things, and the word stream is such a great word that everyone's using it to mean different things. That's kind of an inevitability in our business, I guess. So I think we've seen pretty clearly that Spark streaming it's a mini batch system, and it's designed for really large scalability. It's designed for rich data analytics, even over graph algorithms, machine learning, and so forth. Akka streams is much more focused on first supporting this reactive stream standard, so it has the built-in back pressure mechanism. It has a nice facility for defining graphs of streams, so if you want to fork the processing and have different channels and maybe they join back together, there's a nice little domain-specific language for defining that. Today, it's limited to a single machine system, so it's like a multi-threaded abstraction on top. Well, rather, it's a streaming abstraction on a multi-threaded app. Longer term, it will be something that can use distributed, but for today, you would use it for more local problems like single event handling. Java 8 streams is similar. I know less about this, so don't take this as being definitive, but I believe it's an even more narrowly focused approach to supporting the reactive streams model of back pressure, but in a Java context, layered on top of the existing Java currency primitives. So similar capabilities, but not quite as feature-rich, especially for distributed computing.
Okay, sorry, I was on mute still. That was a good description, Dean. Thanks very much. The next one for you, I guess, since this was part of your slide, is could you could you do a similar could you do a similar explanation of the differences between Akka, Samza, Spark, and Storm, referring back to one of the earlier slides there?
Yeah,
stream processors rather.
Yeah, without taking too much time. I think that really, in a way, at a very high level anyway, you could lump Akka and Samza and Storm in sort of the same bucket as being resilient distributed systems designed primarily for single event processing and routing, whereas Spark Streaming is again for this, basically taking the ability to do what looks like batch mode processing, but at much smaller mini batches, down to like a second or a half-second granularity. So it's interesting, though, that like Akka streams and Spark RDD APIs have sort of a superficial look. They're both sort of very similar to the Scala collections API. So you have your flat maps, your reduces, those kind of methods. But what the infrastructure is doing under the hood, under that domain-specific language, is quite different for these systems. So. Yeah, I would use something like Storm, Akka, or Samza for an eventing system where I need to, like trigger alerts when something happens or something like that. Maybe more of a real-time thing where I need to respond, within milliseconds. I would use Spark for my heavy lifting analytics, my machine learning, my training the models that I might use to detect anomalies or whatever, and training that data in real time. As in the live systems, not relying on static training that I did, say, a week ago and is now growing stale.
Great. Let's see, TD, I think we've got a couple ones specifically related to Spark Streaming for you here. One question a little bit broader to get started is, are there any benefits to using something else like MySQL as opposed to HDFS for checkpointing?
That's a good question. So there are two things. One is in the broader picture of things, there is definitely a benefit to using MySQL because it would improve the performance of checkpointing. That comes to the second point, is that right now we don't support anything other than HDFS compatible file systems for storing the checkpoint information, but that really hasn't proved to be a major bottleneck yet. So we're not really pushing for that as of now. But in future, if we feel the need that we need to really speed up the checkpointing and saving of that checkpointing information as well, then we might look into making the whole mechanism pluggable so that anyone can implement their own pluggable data sink for, be it MySQL or something else, for saving that information. Does that answer the question? Oliver?
Sorry, mute again. On the topic of checkpointing, the question was asked: what's the minimum periodicity for checkpoint saving for recovery? And this is directly from the question tab. So forgive any language that I butcher or if it doesn't make sense.
Gotcha. No, that's a good question. So, so by checkpointing, if you mean the dstream checkpointing, where all the DAG of dstreams is saved periodically into the checkpoint directory. if you're referring to that checkpointing, it is done after every batch. So it is done at a pretty reasonable granularity of every batch. Now, if you're referring to the RDD checkpointing, which actually did not go into much detail in this presentation, that is done at a much lower granularity because that is not checkpointing the metadata, that's actually checkpointing the data, which is a much larger volume of data, right? So that is done much less frequently than every batch interval. So I don't know which one are you referring to, but that there's an answer for both of them.
Okay, great. Dean, one for you. Let's see, where could I find it? In your opinion, how suitable would Spark Streaming be for real-time transactional services such as stock trading? And would you recommend using Kafka and Storm as a more suitable alternative for higher throughput?
So that's interesting. I think what I would say is this. I would probably use Spark Streaming for training my models in real time, but because you have these intervals are, say, down to like a second or so, that's usually way too long to get a response. Like if I had offers coming in and I need to make a call whether I'm going to buy or sell, for that I would want something that's a little more real time, like maybe Storm, maybe Akka. Something like that. So a classic thing, before there was even a mini batch system like Spark Streaming, a classic thing for old MapReduce was to use MapReduce jobs to train your machine learning models, your trading models, whatever, put that model in some format that gives fast retrieval, like in a database, and then have some logic that all it has to do is get the input in real time, do some query against the database, or maybe this model's even in memory, and then make a prediction or a buy signal or whatever, and process it that way. So there's very much kind of a two-level detail of processing here that I think is important to separate. So just to recap, I would definitely use Spark Streaming for keeping these models up to date, for training them in real time, which is kind of an emerging thing in machine learning. But for like making those quick decisions that have to be done in milliseconds or even microseconds, then definitely would want something that's designed for that particular purpose.
Dean,
yeah.
Do you mind if I add something?
Please do.
That? So one thing, so if someone is developing an application like that for trading stocks, one thing to keep in mind is not just the latency of the processing part, but the whole end-to-end latency of in getting the data from whatever the actual source is, the stock market and stuff, to the point where it is actually, the trading action is actually done. So there may be delays right in the beginning of the whole pipeline, like the delays in getting it over the internet, putting it into Kafka, and then getting it out of Kafka and stuff. So there may be like second level latency, like maybe hundreds of millisecond to up to a second kind of latency. And a developer in the big picture needs to be aware of latency as a whole. And then depending on your requirements on the whole end-to-end latency, whether you want the whole end-to-end latency to be tens of millisecond or hundreds of milliseconds, or it's fine to be seconds, you should figure out what are the right tools for achieving that latency in the end-to-end manner. So if, for example, if you may be trading stocks, but if your actions are not really necessary for it doesn't, your end-to-end system doesn't require like a millisecond level latency, it is fine with, let's say, 2-3 seconds of latency, then Spark Streaming might be fine. But if your thing needs of the order of millisecond or 10 millisecond latency, then something else like Akka streams, or which doesn't do batching, or might be a better option, or Kafka plus Storm might be a better option, but then with Storm as well, you need to be aware of its limitations on the fault-tolerant model. So that is what the decision the developer needs to take, but it has to start from the requirements of the end-to-end latency, not just the processing latency.
Yeah, good point.
Yeah, great comments, guys. Thanks. Speaking of latency, there's a question about latency and executor failures. What are the implications when an executor fails, and will recovery occur immediately without delaying the results?
I think that's a question for me. So,
Whomever.
so for executor failures, the moment the driver detects the executor to have failed, it is the switch over to on a different executor to restart the processing is pretty fast. It's sub tens, it's probably sub tens of milliseconds. So tens of milliseconds at max. So the processing has to restart. As part of that processing, sometimes you need to, if you're doing something like a stateful processing, which requires checkpointing the data, that RDD checkpoint I talked about earlier. So in those cases, it requires reading that data back from HDFS, and there the recovery time might be a little longer, maybe order of batch interval or a couple of batch intervals. So that is totally dependent on what sort of processing you are doing. But for something like a simple flat map, nothing very stateful, it should be pretty fast failover.
Probably the biggest thing I would think is detecting that the failure actually happened. That's always the biggest challenge.
Right. Exactly. So that is which is where it gets trickier. Of depending on how things fail. If the Java process fails, probably easier to detect. If the whole EC2 instance fails and there is just no response, can get pretty hard to detect the failure by the driver.
What are some tools that people can use now, or at least start to experiment with for fault tolerance and detection?
Is that in the context of Spark streaming or in general?
Well, in relation to the topic you just covered, TD.
Okay. Some of the tools. So the Spark programming guide has all this information in more nitty-gritty details. So that is definitely worth reading. And then there are examples in the Spark streaming examples that shows how to restructure the code for this purpose. And so you can start off at that point and start testing it out locally. You don't even need HDFS. You can set if you're running it locally on your laptop, or you can just set the local directory as a checkpoint directory and start seeing by manually restarting to see whether it can recover from where it is being left off or not. So I would say that is the easiest way to start playing around with this.
I'll throw this in. If you're really serious about testing it, Netflix has a blog about throwing their Chaos Monkey at Spark Streaming, so you could even try that trick.
Thank you very much. Yes, I forgot to mention that.
Great. Well, let's see. We're actually running a little bit out of time. Would anyone like to make any final comments? Maybe what's a good, aside from what you just said, where should people go to get started?
Yeah, actually, there was a question on that. Let me just throw a few ideas at you. Certainly, the Spark distribution itself comes with examples for most of the features, and Databricks runs, and I'm blanking on the name of it, but basically an examples sort of aggregator of projects that people have done. I also am a big fan of the two Riley books on Spark. There's a Learning Spark book that's very good. Even if you know a little Spark, it's really good for things like performance optimizations and understanding the internals. And there's also, I think it's called Advanced Algorithms with Spark, which is sort of oriented towards data science.
Great. Those should be easy to find. TD, do you have any final comments for our audience today?
I think Dean pretty much covered all the starting points for learning more. I think this was fantastic. The questions were really good questions. Thank you very much, everyone, for listening. Hope you have fun playing with Spark Streaming.
All right, well, thanks everybody for attending. Like I said before, we'll get the slides and video presentation sent out to you ASAP. Uh, as a final note, I just wanted to mention that Databricks and Typesafe have long had an excellent partnership for providing developer support for Spark users. And if you'd like any more information about that, please send us a note, and we'll get you started. And with that, I bid you all a lovely day, and see you next time. Thanks very much.
Thank you.